In this module, we shall define what convergence means. This is therefore the central module of this entire course. So I suggest that you concentrate very well during this module. What we want to do is the following. We are given a sequence xn and we want to define what it means for xn to tend to some x naught or approach x naught or limit of xn being x naught. These are the various phrases we use to describe the same thing. So let's draw a picture to see what we could possibly mean by convergence. So let's draw a picture. This is the real line and we have terms of the sequence xn. x1 is here, let's say x2 is here, let's say x3 is here, let's say x4 jumps back, then x5 is here, x6 is here, let's say this is 0, then x7 is here, then x8, x9, x10. Let's say that eventually it turns out that all the terms of the sequence keep getting closer and closer to 0. Then we would like to say that xn converges to 0. But how do we make this mathematically precise? So we have to define what gets closer and closer to 0. Okay. Now, one of the great principles of mathematics is that instead of solving a really tough problem like this, you try to solve a much simpler problem. What is a much simpler problem that we can solve? Well, we can ask the question, what does it mean for xn to be close to x naught? We will not say xn gets closer and closer to x naught. What does it mean that xn gets close to x naught? Well, now it is subjective. If you were to consider a regular scale, the rulings of a scale are 1 millimeter apart, or in more fancy language, the least count of a scale is 1 millimeter. If xn and x naught are less than 1 millimeter away, then at least from the perspective of this scale, they are very, very close. We cannot distinguish really between xn and x naught if xn is at max 1 millimeter away. So from the perspective of this scale, xn is very, very close to x naught. On the other hand, suppose you have some finer scale and you have attached to it some sort of magnifying glass so that you're still able to see. Let's say the least count is now 1,000th of a millimeter. Then xn and x naught being 1 millimeter apart might not be close to each other. Under the magnifying glass of this new ruler, they might look really far away. Now let's say you have an electron microscope that's able to resolve all the way up to nanometers. Then xn must be really, really close to x naught from the perspective of this electron microscope. So the point is that xn must get closer and closer to x naught, means irrespective of the device that I use, xn must be very, very close to x naught. If you think about it for a moment, if we crudely analyze this, we will be forced to conclude that xn gets closer and closer to x naught if and only if xn is just x naught. If you do a crude analysis of what we are doing here, okay? Because what we are essentially saying is that mod xn minus x naught is less than epsilon for all epsilon, and we have rather proved a proposition that says that in this scenario xn is actually equal to x naught. But wait a minute, xn is not an individual term, it's not just one object, it's actually a sequence. So xn gets closer and closer to x naught does not mean that every term in the sequence xn is closer and closer to x naught. we want xn to get closer to x0 as we increase n. That means, suppose I give you a ruler whose least count is 1 millimeter, and you are able to say, well, x1 may not be 1 millimeter away from x0, x2 may not be, but I guarantee that from x100 onwards, x100 minus x0 is less than 1 millimeter. Okay? So what this is essentially saying is that you provide the ruler or the least count or the closeness or the level of approximation that you desire, then I am able to provide for you a value of n such that beyond that n, all the terms in the sequence satisfy that level of closeness or that level of approximation. So what we have to essentially do is that to show that xn converges to x0, we must show that no matter what epsilon is provided, however small it be, I must be able to provide an n such that whenever the sequence you have beyond that point n in that sequence, then mod xn minus x0 must be less than epsilon. And this is the motivation for the central definition of this course, the definition of convergence. Definition. Let xn be a sequence of real numbers we say the sequence xn converges to the point x0 in R, or limit n going to infinity xn equal to x0, or xn converges to x0. We will use both notations, limit n going to infinity xn equal to x0 and xn converges to x0. Xn converges to x0 is just denoted by an xn right arrow x0. If we can find a function, n from R plus to the natural numbers such that R plus here denotes the set of positive real numbers, such that given any epsilon in R plus, we have mod xn minus x0 is less than epsilon whenever n greater than n of epsilon. So let's see what this definition is trying to say. We have a sequence xn of real numbers. We want to say that the sequence xn converges to x0. The notation for this is limit n going to infinity xn is x0 or xn right arrow x0. To demonstrate that xn converges to x0, we must produce a function n from R plus to the natural numbers. If somebody gives you an epsilon, this epsilon is supposed to be the level of desired approximation, or you can think of it as the least count of the scale. This n epsilon is supposed to be the values, the point at the sequence beyond which the terms of the sequence satisfy this desired level of approximation. That means, given any epsilon, if I choose n greater than n of epsilon, xn minus x0 absolute value must be less than epsilon. Note, this must not be true just for n equal to n of epsilon. It should be true for all natural numbers greater than n epsilon. That's essentially saying in pictorially that if somebody gives 0.01 as their level of desired approximation, x minus 0.01 here, somebody gives you 0.01 as the desired level of approximation, what this says is that x1, x2, x3, so on might fluctuate outside this desired level of approximation, but the moment you cross n epsilon, then all the terms of the sequence are forced to be within this interval x0 minus 0.1 to x0 plus 0.1. So the definition captures our intuition that as you go further and further along the sequence, the terms of the sequence are all clustered nearer and nearer to the desired point x0. Okay. Now let me just make a remark. I have said that we should be able to find a function n from r plus to the natural numbers. The textbook definition states this slightly differently. It states the preliminaries are the same. So you have a sequence xn. We say that xn converges to x0 if given any epsilon greater than 0, we can find n epsilon in the natural numbers such that if n greater than n epsilon, then mod xn minus x0 is less than epsilon. The standard textbook definition just states that given any epsilon, we can find an n epsilon such that if n is greater than n epsilon, then mod xn minus x0 is less than epsilon. The standard textbook definition of convergence and the definition we have given in terms of this function n from r plus to natural numbers is exactly the same. Only difference is I have chosen to treat n epsilon in the definition of convergence given in the textbook as a function of epsilon. The reason is that it clarifies that there is a relationship between epsilon and n epsilon. In fact, you can construct a function that does the job for you. Now, we will unravel the definition, this textbook definition, in great detail in a future module, but for the time being, just convince yourself that the standard textbook definition and the functional notation we have given are exactly same. The reason why I have given a functional notation is because in the standard definition, the order of quantifiers is the key, and it's difficult to appreciate how the order of quantifiers can greatly influence the meaning of a statement. So we will do a deep dive of this definition in a future module. Till then, familiarize yourself with both the definition in terms of a function n from r plus to natural numbers, as well as the standard textbook definition. One more remark. In both definitions, you need not do this for any epsilon greater than 0. You need not do this for any epsilon greater than 0. If you could do it for epsilon in some interval 0 to epsilon naught, okay, where epsilon naught is of course greater than 0. If you can find a function, in other words, if you can find a function from n0 epsilon naught to n, such that the definition of convergence is satisfied for all epsilon coming from 0 epsilon naught open interval, then you are actually done. You can make this function capital N actually from r plus to natural numbers. I urge you to pause the video for a few moments and think about why it is sufficient to just treat epsilon in a given interval from 0 to epsilon naught. You need not consider all possible values of epsilon. Just pause the video for a moment and think about it. I hope you got how to proceed from n from 0 epsilon to natural numbers all the way from n to n from r plus to n. Well, all you do is define n of epsilon to be n of epsilon naught by 2 if epsilon is greater than or equal to epsilon naught. Okay, just define this function. Suppose you have satisfied the definition of convergence for all epsilon in the interval 0 epsilon naught, then define the new function n. I'm choosing to use the same name for convenience, from r plus to n by n epsilon is n epsilon by 2, epsilon naught by 2, whenever epsilon is greater than equal to epsilon naught. Why does this work? Well, if small n is greater than n of epsilon naught by 2, then mod xn minus x naught is certainly less than epsilon by 2. But if epsilon is greater than or equal to epsilon, this is certainly less than epsilon as well. Okay. So the definition of convergence is satisfied for this new function n from r plus to n. Okay. So we will do a deep dive soon. I just want to give one example in this particular lecture. We will study this example in some great detail in the next module. This is, let me just state it as a proposition because, or rather example is better. Let me just state it as an example. Example, 1 by n converges to 0. Okay. Now this might seem obvious to you, but we have a formal definition and we want to satisfy that. What should we do to show that 1 by n converges to 0? Let's display the definition again. You're given this sequence xn. Now the sequence is 1 by n. We have to find x naught, but x naught is also given to us 0. We have to show that given any epsilon in r plus, we have xn minus x naught less than epsilon whenever n greater than n of epsilon. As you would have realized by now, the heart of the matter is finding out what this n function is. So this n from r plus to the natural numbers is the key. How do we find this function? So what do we have to do? We have to find, so first we have to find the function n from r plus to natural numbers. Okay. Now fix epsilon greater than 0. Fix epsilon greater than 0. Now we have to find an appropriate n epsilon. Note that for each choice of epsilon, it suffices if I find out one value for which the definition of convergence works. I can just take all these values together and construct the function n. So what I'm essentially doing is I'm fixing an arbitrary epsilon greater than 0 and I'm going to find an appropriate choice of the value n epsilon. If I can do this for each epsilon, then I have a well-defined function. Okay. So fix epsilon greater than 0. We have to find an n epsilon such that if small n is greater than n epsilon, then 1 by n minus 0, which is just 1 by n, this must be less than epsilon. Okay. I have to find some value n of epsilon such that this is satisfied. How do I do that? Well, by Archimedean property, we can find a natural number n epsilon such that 1 by n epsilon, or rather n epsilon is greater than 1 by epsilon, right? In other words, 1 by n epsilon, this means 1 by n epsilon is less than epsilon. Okay. Now just set n of epsilon to be this n epsilon. Okay. Then by our choice, if small n is greater than n epsilon, then 1 by n is definitely going to be less than 1 by n of epsilon, because n is greater than n of epsilon, which is less than epsilon. That is how this n of epsilon was chosen. Okay. So then this choice of n of epsilon works in the definition of convergence. Right. So the net upshot is we have found a function n of epsilon that does the job for us, and we have used the Archimedean property to do it. Observe that the way this proof is written, you could have used either this definition using functions that I have given or the standard textbook definition. All I have done is I have found for a fixed epsilon, I have found this n epsilon. All I'm doing is I'm just setting n of epsilon to be just this n epsilon. Whichever way you prefer, you can phrase the proofs. It really doesn't matter. Both definitions are identical, and if you understand this particular proof, it should be clear to you why both definitions, the standard textbook definition and the definition in terms of the function capital N from R plus to N, are exactly the same. They are just the same thing in a different disguise. Okay. So this is a very simple example. After a deep dive of the definitions, of both definitions, we will proceed and give many more examples. This is a course on real analysis, and you have just watched a module on definition of convergence.